So, good afternoon or good morning, everyone, and welcome to today's seminar on the resilience of autonomous systems. It gives me great pleasure to introduce my long-term colleague and collaborator, Colin Paterson, who will give the seminar. Colin is a researcher in safe AI at the University of York. He is based in our Institute for Safe Autonomy. And his work considers systems modeling, uncertainty, and decision-making for autonomous system safety. His talk today will be on a very difficult question. Can AI ever be safe? Colin, the floor is yours.
Thank you. Right, okay. Can you hear me okay? And can you see my slides? Great. Okay. So thank you very much for inviting me to talk today. This question was asked of me by somebody at a coffee break at a recent event. And it struck me that in asking it, I wasn't actually sure what they wanted to hear or if they knew actually what it was they were asking. So I gave it some thought after the event, and I decided that there's a number of ways I can answer this. And if I'm honest, the pedantic one was the one I chose at the time, which was, yes, just don't put it into safety critical systems. And then we can guarantee the safe. And it reminded me when I was teaching, I once asked if we could have Python on the computers for the students to learn programming. And the answer was no, because it's too risky. I said, well, in which case, what shall I do instead? And I just got a general shrug of the shoulders from the IT team. Because it's always easier not to put things into play. I guess if I wanted to be a pessimist, then my answer would be I'd start playing with language and say, no, we'll never be able to say that all AI is safe. And maybe that was what my colleague wanted to hear. But I think the best I can come up with after some consideration is the realistic answer, that we as a society will probably agree that some use of AI in some context is more beneficial than it is harmful, and therefore will allow it to happen. But what I realized more than anything else is that we have to think about what the question means. So in terms of the presentation today, I thought I'd look at these things. So what do we mean by safe? What is safety? Then drive down into some of the challenges that AI in particular present to us for traditional safety engineering. And then I'm going to talk a little bit about the work we're doing here at York to give an approach by which we might look at assuring these safe systems. So the first thing I thought we'd look at is what is safety? And we have a trouble here in that what happens is that people often use this word quite imprecisely. And I like this little article that I found online called The Myth of Absolute Safety. And often when people say, is something safe, what they're thinking is, will an accident never happen? And in all but the rarest of conditions, that's a very, very difficult thing to say. And we can only ever really talk about acceptable levels of safety. And what we mean by that is it worth our effort to improve the system any more than it is against the benefits that's going to give us in safety? So we're going to have to get some kind of agreement as individuals, as stakeholders in the AI, of what is acceptable. And in some contexts, that means looking at alternatives or the existing system and saying, can we improve from this? In other cases, it might be looking at, well, what's the nature of the work we're talking about? Because in some places, we can relax safety in some ways because the work we're doing is going to allow us to do that. And then whether we want to talk about it or not, cost starts playing an issue. Not just the absolute cost, but the opportunity cost. It might be that actually improving this one thing's safety is so costly that we can improve a whole bunch of other things instead and have a better societal outcome. Then I think the next thing we always talk about in safety is actually the operational context. And for us, that means that we're making assumptions about where the system is going to be used and how the system is going to be used. And the reality is even though we may have assumptions about the system, when those assumptions are violated after deployment, any guarantees we've made will start to drift away. So we might talk about the safety of a vehicle, but actually we wouldn't expect them to be trying to drive this through deep water. And in fact, the problem is that the context may change around us. We may have no control over that. The picture I've got there is actually from the Japanese tsunami. And I'm sure when somebody was designing the use of these vehicles, having water coming up to your wing mirrors was not one of the environments they were expecting you to drive that vehicle in. So any claims you've made about the safety of that vehicle are suddenly violated under those. But it's not always those severe cases we're in. The reality is that users may not share our vision of how a system should be used. So we might very much expect a system to be safe in a context, and then we release it, people start using it in other ways, and the way they interact with it leads to the system that we have guaranteed being safe being anything but when it gets out into the real world. The third thing I want to talk about a little bit in this, before we even start talking about how we assure safety, is about systems. And I think when we look around with the work we do here at York, we take a very much a system-centric approach to safety. And this picture on the right here shows you the number of systems on a modern automotive car. And in fact, there's another picture I almost used, which showed a similar picture for a Jaguar with the list of manufacturers providing systems for a car. So it's not even that we have multiple systems, we have multiple organizations involved in putting components into one system. An approach there, therefore, is if we're looking at components and saying, is an AI component safe? We have to actually say, well, in a system, is that AI component safe? And without having this systems thinking framework, we're going to find it almost impossible to talk sensibly about safety. We're going to have to start drawing boundaries around the system we are talking about and say whether that system is safe in some context for the operation that we're thinking about. And I think it's really important to say that when we're talking about systems, the questions we ask vary by the level we're looking at. So to think about the car as a whole, safety gives us one set of questions. By the time we've driven down into subsystems, our questions change. So actually safety becomes something that varies by the level we're looking at, the way we define it, the way we talk about it. And a final point I want to touch on is it's not reasonable to say a component is safe without the system, because we could take a component that's been proven and tested and to be safe in one context, put it into a new system, and if we try and migrate that safety argument with us, we find it becomes violated because something about the interactions in that system break our safety case. So they're the three underpinning things we want to think about here. Safety as being non-absolute, operating context, and systems. And then one of the things I want to say where there's a confusion that happens is about this talk between safe and reliable. And we often find that people outside of the safety industry use the terms interchangeably. And we don't. We don't want to be talking about that because it's quite easy to think about systems that are highly reliable but unsafe and vice versa. So a couple of examples might be a circular saw that never fails, and we can say this is incredibly reliable. Every time we switch it on, it runs at exactly the speed we ask it to. It cuts with precision every single time. However, if we leave it out in a workshop without any safety shields, guards, and we get people to use it who are not suitably qualified, we're pretty sure that it's going to be unsafe. And within a time period, the number of accidents are going to increase. So even though the component itself is reliable, actually, if we're looking at that thing, that can be incredibly unsafe. What's maybe a little bit harder to see is that we can have things that are unreliable, but really safe. But this happens often when we have humans in a loop. And we know that, for example, I still remember conditions under which people would look to reboot servers every night. And the reason we were rebooting the servers is we knew if we rebooted them every 24 hours, then we would stave off any catastrophic failures, memory overruns and the like. But actually, if you leave it to run, we know this thing is unreliable. And after 36 hours, the system would collapse with nobody being in there. So safety was put in place by having a human knowing enough about the process to interact with it and say, I'm going to ensure this is safe by taking a mitigating action that I've learned over time. And the reality is that some of those things aren't even written into the design. It's things that are discovered by humans as they start working with systems. And so that safety becomes a part of deployment, even though we've not got it built into our original design. So taking all of those things into account, this is what we try and do when we talk about safety at York. The first thing is we're going to make a claim about the safety of a system within an operating context. One of the big things that we try and do is make sure that the assumptions that underpin those safety claims are made explicit. We look to construct a structured argument to support that claim and then build evidence to show that those claims hold in practice. And I think it's really important to say that we're not just interested in components, but also the process from which those components are produced. So what's AI doing for us? How is this different to anything else we've looked at? Well, one of the things when we look at traditional safety cases is that we have these human operators in there. And we draw a boundary and we say, we use this term quite often, a suitably experienced and qualified individual. And what we're actually doing is saying, here is a rationale and a reason why we can choose to ignore stuff, okay? And without that human, one of the other things AI is going to do is if we replace that human, we're going to have to start doing more and more detailed modeling. Because ultimately, when we're looking at controlling systems, we're looking at having models of the world and models of systems. So as soon as we take a human operator out there, we're going to have to model more of the world, and we're going to have to model that at a much more detailed level of abstraction. If we think about somebody driving a car at the moment, we don't have to worry about things like the surface of the road, things like the small vibrations, because we know a human driver is able to compensate for those low-level changes really very, very well. But if you take that out and you want to now specify all of that dynamics in the system, you suddenly have to go into minute detail about the modeling. The next thing that's maybe very obvious is that we change the way in which we talk about systems. The majority of autonomous systems that people talk about are data-driven. AI has this bigger catch-all, but actually, typically at the moment when people are talking about AI-enabled autonomous systems, they're talking about machine learning and they're talking about data. And there's a huge challenge about decomposing our requirements into data. If we think about the way it's done at the moment, decomposing the requirements to component level is incredibly difficult as it stands. But actually decomposing them to a set of pictures, a set of images, or a set of other data is even harder. And if nothing, it just introduces a layer of challenge that wasn't traditionally there. One of the things that I think really bothers me when people talk about AI is we get this phrase that comes up that says, AI has been proven to be better than a human. The reality of what I'm seeing at the moment is that actually, if you choose a metric appropriately, you can show that a metric is lower or higher, depending on your preference, for a machine-driven system than a human-centric system. But the reality is, when AI fails, it fails in new and exciting ways. And often what we'll find is things that a human would have easily spotted, AI won't. It might do it less frequently, but the reality is the trust erosion is going to be massive. And we saw this with cases when tragically there was the autonomous vehicle that crashed into the lady pushing a bicycle. People said, well, a human would never have made that mistake. It's no good arguing after the event, yes, but look at all these other ways in which it didn't fail. The reality is, if we're explaining these things as safe to humans, we have to be able to explain that the AI won't make human-centric, stupid mistakes, and we can't do that at the moment. We've got a challenge that if we're going to deploy many thousands of systems out into the real world, then we're going to start seeing emergent behaviors, because these identical homogeneous systems are going to start having coincidence of problems. So we're already starting to see screenshots of people showing multiple autonomous cars stranded at the same place in a city, because they all managed to get blocked in one place, and that has a knock-on effect. I worry a little bit about competitors in these AI systems starting to game one another for competitive advantage. If you learn the way one competitor does its AI, and you realize we can have a better AI car by proving that we degrade the ability for another AI car to work, then how are we going to ensure that somebody is responsible for the whole system, not just individual vehicles? And the final thing is, we need to think a little bit about the relationship AI brings between autonomous systems and humans. And I think we're going to have to really think long and hard about what liability looks like when we start to talk about these systems in the real world. So what are we doing here at York about that? So there are a number of pillars that we're looking at working on at the moment. I thought I'd pick out three that we're doing as part of the Assuring Autonomy International Programme. So the one on the left here looks at what we call, which is the societal impact of AI and autonomous systems, and looking at the ethical impact and how we work with humans. The middle guidance document here is written about looking at autonomous systems in complex environments and how we go about talking about the interaction of autonomous systems in those environments. And the one I thought I'd spend a little bit of time looking at today is AMLAS, which is an approach we're using on guidance for the assurance of machine learning for use in autonomous systems. But the whole aim of the program here on Assuring Autonomy was to provide this guidance and examples of the way one might start to think about these problems and give frameworks and practical systems we can look at. So what is this AMLAS that I'm talking about? So it's the assurance of machine learning for use in autonomous systems. And if you go off to our website, and I put the link there for after the talk, you'll find that you can download our guidance document. We've got a website that does this, including we have a tool that you can download for developing your assurance arguments in Visio. So we're trying to make this as much as we can a system that has practical use out in the real world. Before I present this, what I'd like to say is that this is by no means a solo effort. It was a large team effort from us here at York. Plus, we had the input of numerous people working out in industry, giving us examples and feedback on what we could do. And this is what it looks like. So what we try and do is we try over the period of a 6-stage process to drive down from system level down to component level, machine learned component level, and back up to system again. But I just want to highlight, although we've drawn this, there's this nicely serial pattern here. What actually happens is that this is iterative, and the loops can happen. So we can most definitely end up at stage 4 and learning we have to jump back to stage 2 to refine our requirements assurance. So that feedback and iterate that we have in there happens all the time. It's also a process that doesn't replace component development, but it actually works in parallel with it. And the whole idea here is to recognize what happens in ML development and say, how can we leverage that and how can we make changes around that to provide assurance arguments? We understand that there's no point in us telling industry they have to rip up everything they do and start again from scratch. We're talking about how we work alongside them to do ML assurance. So let's start with a little use case, and through the guidance we give several use cases. And what we're thinking about today is the idea of an autonomous vehicle that's using an object detector based in an image processing pipeline. So we get this camera at the top, we have the image pre-processing in it, and then that data goes into an object detector. But what also happens is that that's in parallel with numerous other sensors, and that between them, that information goes into an object database, and there's intelligence in there to do motion tracking, prediction, to update our current belief of the world. From there, there's then a decision planning component, which will reason over that database and that set of beliefs to come up with a route plan, and then that will be fed into a set of actuators that deal with the acceleration, braking, steering, and do the actual actuation of the vehicle. So if we want to think about this at the top level, what we're actually saying is what can happen that requires this system to become unsafe? Well, unsafe actions only happen through actuation. And we're actually trying to say what part does object detection play in moving into unsafe states, and how is that part of it? So you can see from this already, we can't just talk about an object detector in isolation. We have to have understanding of the full system. So what we do is we start in this very first stage, and we look at this. This is how we describe all of the stages in AMLAS. This one has two activities. The first is defining the assurance scope for which the ML component plays a part. And we start by having these sets of artifacts. So activity one takes 4 artifacts. It takes the system safety requirements that are written for the top level, a system description, an environment description, an ML component description. And from that, it's going to generate some safety requirements that are allocated to the ML component before we move on to stage 2. And the whole purpose of this is to define the scope of the safety assurance with respect to the ML component. And what we're looking to do is write a top-level safety assurance claim for an argument we're going to make over the safety of that one component. So one of the artifacts that might be the input to that is the system-level safety requirements. And one of those requirements might be the vehicle shall obey all traffic signs. And specifically, let's think about the requirement with respect to stop signs. And we'd say the vehicle must recognize all stop signs in sufficient time for the vehicle to come safely to a halt. We're not discussing the technology at this point. This is not about ML. This is not AI. This is purely a system level safety requirement. The second artifact that feeds into this is the component description. So if we think of this conceptually, what we have here is an object detector. And the way our object detector is going to work is it's going to take an image as the input, so our original image, and it's going to draw bounding boxes around a whole bunch of objects that it recognizes in that image. And for each one of those bounding boxes, it's going to give us a single label for the object it's most likely to be. So we have a component description at an abstract sense. We have our system level description. And from them, what we then do is we start to decompose down to what the component needs to do. So the first requirement here is talking about the ability of the component to correctly classify objects. And you can see what I've done is I've written this out. The object detector component shall correctly detect any stop signs present in the planned path of the vehicle in its correct location in 95% of frames where a stop sign exists within 80 meters of the vehicle. Because of the nature of the environment and the nature of the technology, we know we can't get 100% accuracy. So where does 95% come from? 95% would have to be argued over the pipeline in which the system exists. 95% is a figure that we've argued with the frame rate of the videos that is coming in, the amount of time it has to recognize it, and the way that our object updating works in our database. 95% of frames allows us enough information to reduce the uncertainty to a point where we can make confident predictions about that component, about that object in the space. Similarly, 80 meters isn't picked out of thin air. It's talking about road conditions. It's talking about the dynamics of the vehicle. How long does it take? At what speed is it running for it to be able to look in this? All of this will be evidenced through our argument to say, this is the reason we've chosen these numbers to go into our argument. We also know that what can happen with these kind of components is that we can get false positives. So our second requirement is saying, you don't just stop, okay? We're talking about systems where having a false positive also carries a safety risk with it. Again, similarly, we're calculating the probability of stopping, unfortunately, and how we can mitigate it. And we come up with this case, an example might be 99% of frames, you're not going to have a false positive appearing. And then this final one is to do with the fact that we understand that this is living in a world where road geometry matters. We're not just saying, can you identify something? We understand that there might be stop signs in the road that don't apply to us. They're on different slip roads or whatever else they are. And therefore their location in the image is important, because if it was too far to the left, we might stop, unfortunately. If it was too far to the right, we might assume it was not for us. And so therefore we've done a calculation of what that might mean. And all of these things then get stored in an artifact that becomes part of our evidence for our safety argument. And in fact, that's what we then do. We then look at instantiating a pattern. So the second thing we say AMLAS talks about processes, AMLAS also gives you patterns. So this is a pattern in which everything in curly brackets is something that will need to be filled in by the safety engineer. So we start with a goal. So our goal, our safety claim is that the ML component, in this case, a object detector, satisfies its allocated system safety requirements in the defined environment. And the box is labeled with C around the side of the context in which we're operating. So again, this is where these artifacts come in. So artifact B is the description of the operational environment, C, D, E. Again, these are the artifacts that were the input. They become our evidence. And they might be just a hyperlink to a massive body of evidence that's been gathered over a period of time. Might be a simple document, might be a simple link. On the right, we have this thing A. Again, this is this idea of making assumptions explicit. So we have this assumption in there that in writing this, we were able to get a full set of safety requirements allocated to the ML component. If we don't make that assumption, if we're not working to that assumption, there's no way this argument can hold. And then what we say is, well, what's the strategy we're going to use to prove this goal? And the answer is, well, we're going to argue over the development and the deployment of the component. And again, there will be, as you move through the AMLAS process, you're going to fill in each of those patterns and follow each process to complete it. Now, we're not going to have time to go through all of the pattern today, but I thought it was worth pulling out a couple of interesting bits that maybe people will have questions about or want to raise further questions on. So the first thing is, I talked about 95% accuracy, I've talked about distances. Of course, once you get down to the technology, once you get down to the way in which the component works, they might not be the right questions to ask. So the second stage of AMLAS is about transferring these questions down into the tech appropriate questions to enable us to validate and verify the requirements that we have. And an important part of that is ensuring that we maintain the intent of the original requirements. So here we've got an example of the mean average precision for the component in detecting a stop sign should be no less than 0.9. Because of the object detector we are using, we don't talk about position, we don't talk about accuracy as we do about simple classifiers, we talk about mean average precision. So what we're going to have to do is make an argument here about why 0.9 mean average precision is sufficient to capture the three requirements we had at the earlier stage. So that if we were to change the technology used in that component, we might have a different set of requirements appearing there. And again, there will be multiple requirements appearing at this stage. I'm just pulling out one to explain that to you. And again, you can see the pattern on the right. And if I look in detail here at the top of that, we can see how not everything has a single goal, but this one here talks about allocated system requirements. And it talks about splitting that into sub-goals. So in some of the patterns, we have these sub-goals. We can talk here about how the model itself looks and what about the model and the data. And we can talk about that the safety requirements are a valid development of the allocated system safety requirements. And again, we're adding the context and we're adding our assumptions and our justifications to the pattern as we go. The little rectangles on there, which is the called ACPs, assurance claim points, are where they're, again, new patterns that AMLES talks about how you would develop those. The final stage of AMLAS is where we start to talk about deployment. Because one of the things is that we're well aware that there are challenges about looking at putting AI systems into deployment, because the world does not sit still. And we can only talk about the safety of deployment if we're actually going to start thinking about how we deal with changing systems. I will warn you that this is, if you go to the website and download AMLAS, you're going to get AMLAS 1.0, and this is a different pattern, which will be released in our a journal paper early in the new year, which is the next version of AMLAS, in which deployment has been refined a little. But you can see here that the idea is to talk about some pieces that are specific about using ML in the wild. So one of the things, for example, is that we do all of our development of AI traditionally on large hardware, using large libraries. And then when we come to deploy them, we often use edge computing, which means that we have to do things like model quantization. We need to do things like using lighter weight libraries. So we need to have arguments over why moving from one domain, one type of technology to the other doesn't violate everything we proved in our testing phase. So that's one thing we're talking about. We talk about the fact that how we're going to monitor this, how we're going to make sure that where we've made assumptions, those assumptions aren't violated in the real world due to us releasing AI into the real world, amongst other things, but also things like environmental change. So we're looking at the way that we might monitor and test our ML deployed component as we go, as we put this out into work. So I realize that's just a very quick overview of AMLAS, and I'm happy to talk in detail about more of it today or later. But I did want to point out three things that AMLAS is only starting to look at. And I think these are three big challenges we have for AI safety more generally. The first is moving beyond physical harm. There's a really big conversation happening now in what it means for AI to cause harm in non-physical systems. So if we think about social media, we think about the use of AI in doing job allocations, loan approval. All of these things have huge scope for causing problems to society at large. And we're only beginning to see how we might reason about those. And I think the reason team and Radu have started to look at how we do trade-offs between social, legal, ethical, empathetic, and cultural harms. And that's something that's going to have to develop extensively if we're going to get trust built in society for AI systems more broadly. I think autonomous vehicles is something where we've seen a lot of talk, but it's by no means the only place where we're going to see AI happening. I think the second place we're going to see a huge amount of work having to be done is in dynamic systems and in the changing world. It is not clear at present how we're going to build systems that are able to tell you when they're moving beyond their safe environments, and more to the point, what we might do about them. If we're not careful, we're going to hit a point where we've deployed AI systems that it's very, very difficult to turn off. And if we don't have an off switch, then we need to be pretty confident that they can change as the world changes around them. And the third one is about regulation and legislation. I think there's a huge piece of work to be done here to make sure that when we're asked questions like, will AI ever be safe, that people understand what that question means, not least of all regulators and educators and policymakers. And I think if we don't engage with them to talk about what AI safety really looks like, then we're never going to get responsible research and innovation out into industry where it needs to be, to make sure that we end up with safe systems that we can use. So, will AI ever be safe? I think we're going to end up agreeing that some AI will be more useful than it is harmful in certain contexts. And I hope that's true, because I think AI has some huge potential for making life better. I really don't want to be the person who says, you're not allowed to install that here. Thank you.
Thank you very much, Colin, for a very insightful talk. We have 20 minutes or so for questions. So any questions for Colin? I'm happy to start with a question until other people formulate theirs. So maybe one thing I wanted to ask Colin is whether you think there is any merit in proceeding in some sort of baby steps with developing these applications and trialing them in stages, or would we be able to learn in that way how to build more useful application over time, over multiple stages and iterations?
I think that thanks, Rado. I think that's really interesting. I think the challenge is saying what the baby steps might be. I think thinking back to that idea of context and system, I think that the reality is what we need to be able to do is use these in constrained environments where we are confident that we can monitor appropriately what's going on. I think that putting these things out into large open world problems is too big a step initially. So I worry about using these without guardrails in place, whatever they might be. So I think one of the baby steps is, at the moment, we should always be very clear about how we turn it off. And I think that the other thing is understanding about where the liability is going to land, and that people understand the implications of rolling these things out. So yes, I want to see these things working, and we're starting to see some nice applications in healthcare that are being done, because I think they have a lot of experience in doing trials in a responsible manner. I worry a bit more about some of the other application areas.
Thank you. Richard?
Sure. Thanks, Colin, for a very nice talk. And these won't be questions like at your PhD project. First of all, I think I agree that medical is a great domain in which to investigate this further. Some of the work we've been doing with a company called Arrayus has led to a great deal of safety and assurance maturity, and potentially some desire to investigate AI, machine learning specifically. But having that background in safety to begin with makes them aware of risk. And that's sort of the basic level of maturity you need to do this. So I have a general question to start with, and that is, as a result of the work you've been doing, do you see it being possible to move to a state where you can actually give some guidance on how to better design machine learning components so that it's easier to assure the systems in which they're embedded?
Thanks. Yes, I think it's possible. always with these things, it's about getting enough resource and enough people and enough time to do them well. I think there's quite a lot of work to be done out of the requirements engineering community to talk about what does good look like. So I think Radu and I, along with colleagues, wrote a paper on what we felt was good in terms of data. So we came up with a way of talking about desirable features for data. I think similar guidance on desirable features for post hoc explainability in a context where you're actually looking at those sort of things. There's been some work in that area. I think that one of the areas where I think there's huge steps to be made is in incremental engineering. As a community, we've got vast experience on how we do model-driven and incremental engineering in software, and how we talk about those things, and how we talk about what does it look like to improve something. I think there's a huge step to be made in AI to talk about, well, what does that look like? Because the best of my knowledge at the moment, doing incremental model design in AI is still an open challenge. So I think any tools that look around, how have I changed a model? So if I'm looking to improve a model in light of accident investigation, how can I be sure that I haven't just created a differently bad model is a really tricky thing to do. So things that talk about additional information out. So we've started to talk here about things like, maybe rather than saying I have a high confidence that this is a car, maybe actually you could give me some more information about the environment in which you're making that decision. You know, so actually saying, I've got high confidence that I'm spotting a car, but by the way, your vision sensor is currently covered in mud and not working particularly well. They're the sort of things that I think from requirements engineering might lead to better component design in the first place.
That makes sense. And I think there's, especially in something like automotive, you could see all kinds of ways in which you could make the contextual information available about the environment in which to enrich your decision making and enrich your confidence in the model. That's really nice. Radu, do I have time for another really quick question?
Yes,
I don't want to hog the... Okay, thank you. So I was intrigued by your discussion on the modeling side of things, as you might have guessed, and that it will become necessary, or potentially necessary, to model more with more detail. And I get that. I think that makes sense. But I was wondering if you'd thought about what you can not model. Because one of the things that I've learned is that you start working on a new problem, you bring your modeling calculus and tools with you and your traditional way of modeling, and then you add to that. But then there has to be a phase where you drop stuff, things that are no longer relevant to the purpose that you have in mind. And have you encountered this? Or do you have any insights about this for ML in particular?
So I haven't thought about it explicitly. I think one of the challenges that we have with the current way in which ML is done is just throw everything at it and get the biggest model possible. I think, I mean, I know it's a ridiculous example, but ChatGPT-4 has got over 1 trillion parameters in it. It becomes very, very difficult. And we know that if you model it the incorrect level of detail, and I'm not just saying too abstract, but actually too detailed, then you end up introducing noise and you end up introducing artifacts that cause you problems at other levels of control. So appropriate levels of modeling are very, very hard. I'm not sure at the moment how one might bring in, and I'm really interested to do work in this area to see how you bring in real engineering insight into those things. And I think the reason it becomes tricky is as soon as you say AI doesn't see the world like you do. So if you bring in things that make perfect sense to a human, that's helpful as long as your engineering design supports that. But if you bring in that insight and the AI doesn't use that because it has become over-reliant on edge detection in high dimensional space, then it's not meaningful modeling. So I think there's this disconnect in terms of where the models are being drawn and how the models are being drawn and how we're wanting to understand them. I think there's some really interesting work on model reduction in AI that I think I'd like to see more of. So yes, you can build a model that's got 1 trillion parameters, but can you actually get something that does the same work on a lower dimensional space that actually gives us a more analyzable view of the system, even if it's running in parallel, for example, would be great.
Thank you. We should talk more. We've been looking at some of these issues here.
Yeah, great. Thank you.
Thank you for your answers. Thank you, Radek.
Right, so Colin and then Kirsten.
Hi there. Yeah, no, that was a really interesting talk. So I had to unfortunately step out for 5 minutes or so. So apologies if you already talked about this, but this actually kind of falls on quite nicely from the previous question, which is, I suppose one of my, I don't know if I want to use the word concern, but one of the things I've kind of always been fascinated by is this idea that, of course, as we expect more and more of these autonomous systems to be deployed in the real world, they'll be interacting with each other as well as interacting with us in these sort of hybrid teams. And we are now going to be having these sort of complex systems. And of course, I highly suspect we're going to get these emergent behaviors, right? And this is one of the things, of course, you can't model. You know, like I came from a swarms background, and while these are really useful properties for robust and resilient systems, we can't necessarily predict or verify them very well going forward. So I was just wondering if you think there's like an effective way, I suppose, of at least doing some sort of like either forecasting or prediction detection sort of system to help stop maybe these suspected dangerous emergent behaviors from actually, actually occurring or getting worse, I suppose.
So I think that the key thing here is not to think of AI systems in isolation, but to think of the whole system. And I think even if we could talk about how 20 or 30 drones working in isolation in a factory might lead to emergent properties, it's not going to get away from the problems of emergent behavior of AI and human teaming. One of my favorite examples of this was nothing to do with AI, but it was the introduction of barcoding into hospitals for prescribing. And it changed the way that nurses took medicines off the shelf. And what that led to was a different mode of failure. It didn't mean the system was any more safe overall, it just meant it was failing in a different way. So I think emergence, you're absolutely right, is a really critical thing that we have to be talking about. And I think that's one of the big challenges for post-deployment and making sure these systems are safe, because it's not always your agent that's going to be the problem. It's going to be the coincidence of the AI agents with each other and with the environment that's going to lead to unsafe states that we need to be able to talk about. So I think that's about monitoring processes more widely than development. I think we must think about it in advance, but I'm not convinced at present you're going to build a system that's going to avoid it from the off.
Great, thank you.
Kirsten?
Thank you. Hi, Colin.
Hi,
very,
Kirsten.
very interesting talk. Thank you very much. Really, really inspiring. I wondered if we step a step back and think about designing for assurance or safety, what opportunities do you see there rather than doing it as an afterthought?
Oh, absolutely. So thank you, Kirsten, for bringing that up. So I think that one of the things we want to encourage people to do, certainly with the AMLAS thing, is to build this into the pipeline. And what we're trying to say is, so interesting, when we were first talking about this, a very simple thing that I wanted to get in there was a AI development log. Thinking of my software background of, when you're doing testing and you find bugs and you bring these things in, you want a log of saying, well, we tried this, this is what we found out the problem was, this is how we fixed it, this went forward. I thought it was relatively straightforward to say, well, what you want is something that talks about those sort of things in terms of your AI development, and this is what we want. Talking about to people who are doing this, this isn't standard practice necessarily in the way that many of those teams are doing their exploratory design, shall we say. And I think you need, so there's one thing is to encourage people to say, generate artifacts that are going to make your life better. But I think it's quite a different thing to educate teams on what it means to do safe AI development and have safety as a first-class citizen in your development pipeline, and say this isn't just a tick box exercise of doing this, but actually there are real world benefits of having this foundationally in the way you're doing it. So yes, what we're wanting to do is train people to take that approach that says, just as maybe 20, 30 years ago, we had to force people to talk about how you would design software in a way that was maintainable and you could reduce your tech debt as you went forward and all those sort of things. We need to start talking to people about AI isn't just about doing lots and lots of experiments to churn out a model and say, well, there you are, it's done. So yes, I think it's going to be baby steps in persuading the right people to make the right changes. But I think I mean, the vision is that we come up with development processes that support the development of safe AI.
Yeah, thank you very much. I agree. At the moment, what I see and also hear from friends who work or previous colleagues are now, working in this industry is this sort of construct by correction mentality. And if you look decades back, that was the way software was. Well, this is still the way the software is done, but the software that we use to fly aircraft is not done that way.
Correct.
And that's the important thing, right? There is a lot of different approaches to designing software systems, but there's only a handful or, very limited number that we are content with in order to let them fly aircraft.
Yeah,
and
absolutely.
I think that sort of step back to say, hang on, we don't know where this is going. But if we were to consider this up front, what would happen? What is enough AI? And trying to gain confidence about the AI that is absolutely necessary in these safety critical systems, and get to grips with that, and maybe less is more in terms of AI, with balancing it out with the assurance needs that we have. And so correct by construction or something towards that rather than construct by correction is something that requires a fundamental reevaluation of how we do this. And a guideline and processes that should be employed in the development process. Yeah.
Yes. Thank you.
Thank you.
Right. Maybe another question from me, Colin. You emphasized how important it is to not expect these AI control systems to operate correctly outside their operational design domain. Now, humans are particularly good at spotting when something unusual is happening around us and realizing we are outside this ODD that we are trained for. What mechanisms do you envisage that AI-based systems could employ to achieve a similar capability to recognize out of ODD scenarios they might be facing?
So I think there are some trivial ones that, let's say, we can build in there, which are things like geofencing and various other things that might talk about things like this was designed to be used in a particular country, outside a country. Use on not everything has to be complex. Of course, we can have things like sensors for moisture, sensors for light. We can look at things like that that say, okay, we're moving outside of those things. But I think more generally, when we've got things like sensor fusion, making sure that we look at things like I know that's not there are certain manufacturers who want to rely on vision alone, but if you're in safety critical contexts and you know that using LiDAR and vision together is going to give you the ability to avoid things more reliably. And then we're into things like extra analysis techniques. So using verification in multiple contexts. So instead of relying on one form of verification, using multiple models in multiple verification techniques to look at where we currently are in the space. I know we've done some work on that. Looking at methods that are able to identify drift. So we're trying to do some work at the moment that talks about degradation of image. So in a general sense, to say that the images coming in are degraded and you should start to move into a different mode of operation. So we may not know precisely why it is degraded, but we know it's degraded, and that might be due to sensor noise, it might be due to atmospheric conditions, it might be due to something else. I think we're always going to hit situations that we can't make sense of, and it's why I suspect that going into some of these large open environment problems straight away is difficult. I think one of the things is that many of the problems we're seeing about driving in the open world, in the early 90s, we could drive autonomously for a good percentage of the time, and there was a small percentage of the world we couldn't deal with. It's a slightly smaller percentage of the world we can't deal with, but we still can't solve those problems, is the honest answer. So I think there's things we can do about clever vision techniques. There's things we can do about monitoring more precisely. I think potentially you could do stuff about emergence of behaviors by inter-agent communication and looking at patterns of change across those. I think we have to think about data coming in as a stream rather than having single shot. But it's not going to be one technique. We're going to have a bag of techniques that we can use to give sufficient evidence for all but the simplest of systems.
All right, thank you again, Colin. I see there are no more questions and only 1 minute left, so I suggest we stop here. Thank you again, Colin, for answering these questions and for the very nice talk, and thank you everyone for attending and participating in the discussion.
Thank you.